In this question, we have a quartic function that's been sketched, as indicated, coming up, down, and then back up, and a line L with equation y equals mx plus c. And we're told that L touches C at two places, therefore it's a tangent. But not only a tangent in two places. And we're asked to explain why this here is true. So when I look at the left-hand side, I can kind of see that it looks like they've set the two equations equal to one another. And I think that's a good starting point anyway. If we're ever trying to find solve for x, which we've got an equation involving x. So when C and L intersect, we've got the x to the 4 minus 10x cubed plus 33x squared minus 34x will equal mx plus c. This implies that x to the 4 minus 10x cubed plus 33x squared, and it's going to be minus 34 plus mx minus c is equal to 0. And I've managed to get the left-hand side of this equation. It's just that how do we get this part here? Well, we've got to think about these points P and Q because they are the two solutions to this equation. The solutions to this are P and Q. But they are double roots since L is a tangent at both points. And therefore, x minus p squared, x minus q squared is equal to 0. Because, this is how you get a solution with double roots. And the result will follow. I feel like this is enough explanation. The main thing is, setting it equal and rearranging to get 0, and then discussing and saying, well, P and Q are solutions. So it must equal, if we were to factorize it, it must equal x minus P, x minus Q in some form. But because it's a tangent, you get a double root, then it must be that it's these two squared equal to 0. And that's that bit done. In part B, we're told that the finite region R, which is indicated, is bound by C and L, and we're asked to show that we get this as the area. We've got to think carefully about how to calculate this. If I integrate under the curve in this positive region and then subtract the straight line, then I will indeed get this bit here. But I've got to think carefully about the negative region because remember, when you do an integral, you get a negative, I don't want to call it a negative area, but a negative value, which you then need to make positive if you're doing the area. But here's the thing, if you subtract the curve, if you do the curve minus the line over here, you'll be okay. Now, if you do the curve minus the line over here, and because the line is actually more negative, what you'll end up with is a positive number because you'll get this bit here, which will be negative, and then you'll subtract everything over the line, which is also negative, and the result will be a positive value. And what I'm trying to convince you of is that we can do the following. We can integrate from, remember, we're integrating from P to Q, and it's going to be the curve minus the line with respect to x over the whole region. Now, if you're not convinced by this, and I've got to say, when I did this question, I had to think about it and play around with it a little bit to convince myself. I will show you at the end, or actually at the end of this part of the question, why we can definitely do that. But this is our starting point for this question. So that will give essentially what we had um, at the in part A. We had x to the 4. I want to show this in full. So it's going to be, remember, in part A, we had this and then we subtracted the line. So we're going to get the same thing. It's going to be, actually, maybe I can just copy it and bring it down. So it's going to be this. But the key thing is not to start integrating this because we were given a massive clue. We were told this function can actually be written as x minus p squared, x minus q squared. And we're also told to integrate by parts. So that was a big clue because you would never integrate this blue one by parts. So that's where we're up to. I hope I've convinced you about that. We're finding the area between the two curves. It makes sense for this region. You have to really think about it for the negative region, but it is still the curve minus the line to get the positive area. When we're subtracting them, we get this blue this blue expression, which we've shown in part A is the same as this green expression here. So let's integrate it by parts. It's not going to matter which one we call u and which one we call v prime, as long as we're sort of consistent throughout. So that can be u, that can be v prime. U prime will equal 2 x minus p. V will equal a third x minus q cubed. So then we'll get uv, which will be a third x minus p squared, x minus q cubed, evaluated between q and p, minus the integral from p to q of u dash v. So it's going to be 2/3 x minus p, x minus q cubed. Now, normally I would do this integral before I substitute in, but actually, if we look at this here, when we substitute q in, this is going to be 0. When I substitute p in, this is going to be 0. This here is just 0. So now I'm going to do the same again. But when I said being consistent, this is now going to be u. I need to make sure it's this way around to continue to simplify it, and this will be v prime. So u prime will just be 1, which is great because we're trying to make things simpler when we integrate by parts. And v is going to be a quarter x minus q to the 4. So I'm going to get minus 2/3, because I can just bring this out. And then it's going to be uv. I'm going to change this square bracket. So there's a square bracket here, uv evaluated at qp minus u prime v. So we're going to get a quarter x minus q to the 4. And again, this is going to disappear. This is just 0. So where am I up to? I've got 2/3 times a quarter, which is 2/12 or 1/6. I've got 1/6 as a double negative, so that cancels. This. I'm going to divide, so add 1 to the power, and divide by the new power, which will give me 1/6 and 1/5, so 1/30 overall. I'll put all of this inside a square bracket. When I put the q in, I'll get 0. So then I just need to put that'd be minus, so it'd be 0 minus 1/30 p minus q to the 5, which is nearly what we want, but we'll go all the way back here. We wanted q minus p to the 5. But that's just because the minus is dealing with that. So it's 1/30. And then if I bring that minus in, it will become q minus p to the 5. And we've done it. So maybe I should have written area of R equals. Now, before I move on, I just want to completely convince you that I could do this, that I could just do the curve minus the line. And I'm going to split this up into different integrals. So if I wanted just to find up to here, right, I've got p here. I'm going to call this k1 because that's where this bit crosses over. And then here I've got k2. So I could write down that the area of R is equal to, and then I'm going to integrate from P up to K1. And here, right, I need to think really carefully. So if I do the line minus the curve, then that would give me this bit here, but it would be negative. And so to make it positive, I would need to put a minus in there, which, by the way, is the same as C minus L without it. Then I would add the integral from K1 to K2 of this bit here. So now if I integrate the curve, then I'm going to get this bit above the axis. And then if I integrated the line, I'd get this, but it would be negative. So I need to minus that essentially. So it's still C minus L. It's consistent throughout that it's C minus L. And then the last bit, I'm integrating K2 up to Q, and that is clearly C minus L. So all I'm trying to do here is convince you fully, because remember, I can then bring it all together because I've got the integral of C minus L from P to K1, K1 to K2, and K2 to Q. So it's the same as integrating all the way up to P to Q. That's one of the rules of integration. So I hope I have convinced you, if you weren't already convinced, that I can basically go straight to this. I don't think it's obvious that you can do that, and it's just because they cross over and it all works out with the negatives. But yeah, we do get this as the answer anyway. Given that this is the last question of the paper and we're really near the end, then actually part C is extremely nice because this is simply basically an expanding bracket question. So start from the left-hand side. And then I'm going to expand the x minus p part. So it's going to be x squared minus 2px plus p squared. And the same for q. Technically, these are identities. Then I've got this double bracket to sort out. It's going to get x to the 4 minus 2q x to the 3 plus q squared x squared. That was dealing with the first term and doing cross multiplying. Now I'm going to deal with this one. I'm going to get minus 2p x cubed plus 4pq x squared minus 2pq squared x. And this last one, and it's starting to look a little bit like this. Just need to bring it together. So I've got x to the 4, which I've dealt with. And it's going to become minus 2p plus q x cubed when I bring this one together with this. And so I've dealt with that, and I've got what they had there. Okay, now I'm being asked for the x squared one. So here I'm going to get p squared plus q squared plus 4pq lots of x squared. And that's going to be my s. I keep going, so then I'm going to get minus. I can factorize out the p and the q. So it's going to be p plus q x. If I bring this one together with this, and this bit here is going to be t. And then finally, it's plus p squared, q squared, and that bit is going to be u. So we've done it. I just probably it's best to just write these down one last time. Yeah, there we go. We are asked finally in D to oh, let me just scroll back to the top, to use parts A and C to find the value of P, Q, and the equation of L. So essentially, we have two different expressions for this thing in here, and therefore I can set this that I've just found, including what S, T, and U are, I can set it equal to this, which is what I've brought down here. Okay, and therefore this is part D. So S, remember, is the expression in terms of x squared, which was this, and I can set that equal to 33. T was the expression for in terms of x, and I can set that equal to 34 plus m, because I believe it was minus tx. And then that just leaves, I've got minus c, and I've got a plus u. So actually this here is going to equal, this is going to be minus c. So using A and C, we're going to get this. And I have something else actually that I've not yet written down. And that was, remember, I've got my x to the 4, but I've also got this coefficient for x cubed. I've got that 2p plus q must equal 10. And that's going to help us with our first result. So therefore, P plus Q must equal 5. Now we can use that um, to help us. So P squared plus Q squared plus 4PQ is 33 as above. I can actually factorize this partially. It's going to be P plus Q all squared plus 2PQ is equal to 33. This will give me P squared plus Q squared plus 2PQ. So this will all work out. And I've just said that this here is equal to 5. And therefore 2PQ. So this will be 25. And therefore 2PQ will equal 8. And PQ will therefore equal 4. This is good. So I've dealt with S, and I've dealt with what other one I've dealt with? This one here, but I can actually use them both together now. So P plus Q is equal to 5, and P must equal 4 over Q. And essentially I've got myself some quadratic simultaneous equations to solve, because if I replace P by 4 over Q, I get 4 over Q plus Q is equal to 5. That means if I times through by Q, I'll get Q squared minus 5Q plus 4 is equal to 0. Factorize this. Q is equal to 1 or 4. And from this, we would get that P is 4 or 1. But remember, we were told right at the start that Q is going to be bigger than P because of where they are. And that means Q will take the larger value. P equals 1, Q equals 4. I should probably just say reject since Q is bigger than P. So we've dealt with most of the equations. We've now got that minus C is equal to P squared Q squared. So C is equal to minus P squared Q squared, which is going to be 1 times 1 times 4 times 4 minus 16. And then finally, we've got this bit here, this 2PQ times P plus Q is equal to 34 plus M. Therefore, M is going to be 2PQ P plus Q minus 34. Which is 2 times 4 times 5, which is 14 minus 34, and hence we get 6. So line L is y equals 6x minus 16. We found P, we found Q, we found line L as required. This is a really neat question because at no point did we actually integrate the function. We used this, obviously the question guided us, but used this clever little technique to set it equal to this thing factorized, even though we didn't know what P and Q were. We found the area in terms of P and Q, and obviously we could now, we could substitute those values in at this point if we wanted to. And then we actually found P and Q not by solving a quartic equation or anything like that. We didn't even know the equation of the tangent, did we? But by like expanding the brackets, equating them, and solving a set of simultaneous equations, essentially. So I really like that, really different. Because it's so different, that's what I suppose makes it somewhat challenging. Part B with integration by parts is probably the most challenging, but I hope you enjoyed that question. There's a lot to it, isn't there? But it's a good one.